We're going to continue to talk about equilibrium after watching the other video, the one that was introducing the concept of equilibrium by using the analogy of coins being moved from one container to the other. And here we're going to introduce some basic concepts and definitions about equilibrium and the principle that's called the Le Chatelier principle. So in general, when we normal English, let's say, not in a chemistry class, by equilibrium we mean a state of balance. Now there are two main types of equilibrium that we can think about: static equilibrium and dynamic equilibrium. So you're probably familiar with this concept in mechanics. On the left you see one of those toys that you can see on a playground. I think it's called teeter-totter or something like that. And basically, when there is a balance between the position of one of the two kids with respect to the fulcrum and the weight of the child, you reach an equilibrium, but this is a static equilibrium. Nothing moves. The position is like a scale, basically. The position of the object stays constant. On the right, instead, you see an example of a dynamic equilibrium. That would be what happens when you have like a child in a mall and they start, going backwards on an escalator. So the escalator is coming down, and the child try to keep up with the escalator by climbing it. So everything is moving. The escalator keeps moving, the kid is moving, it's walking on the escalator. But if an equilibrium is reached from the perspective of an observer who is external to the elevator, the position of the boy is going to stay constant over time. So this is an example of a dynamic equilibrium. Things keep moving, but the relative position of the objects is staying constant. So what would be the parallel in chemistry? An example of a static equilibrium in chemistry would be an irreversible reaction, a reaction that proceeds only one way, like burning. You always go from wood to ashes and CO2, and you never come back the other way, right? So this is acid-base reaction that you've seen multiple times, both as an example in class or in the lab, where you have sodium hydroxide and hydrochloric acid, a strong acid, a strong base, you form a salt, NaCl, and water. And this is an irreversible reaction. So by the end of the reaction, if you have equal amounts of the two reagents, you have no sodium hydroxide left, no hydrochloric acid left. All you have is the sodium chloride and the water that you've formed, and there is no reaction anymore. So that would be a static equilibrium. What we're going to talk about in this unit is a dynamic equilibrium. That would be what in chemistry we call equilibrium. So whenever you hear the word equilibrium in chemistry, is always a dynamic equilibrium, and we have a special symbol. We have the double arrow. And the classic example is the synthesis of ammonia that we will use multiple times as an example because it's sort of the poster child of equilibrium and is also very relevant from the industrial point of view, in which by the time you reach equilibrium, what stays constant is the relative amount of ammonia, nitrogen, and hydrogen. So the ratio between those. But the reaction both reaction keeps going. So you still have new molecule of nitrogen that are reacting and becoming ammonia, and ammonia decomposing back to nitrogen and hydrogen. So a chemical equilibrium is a dynamic process, and by the time you reach the equilibrium, what stays constant is the relative concentration of reactant and products. This does not mean that at equilibrium the concentration of the reactant and the products is going to be the same. It could happen occasionally, but it's actually a rare occurrence. Normally they are quite different. It was the same with the coins. By the time you reached equilibrium, the container that was labeled as products had twice as many coins as the other container. So the amount was not the same because the two kinetic constants were different. One was 1/2 and one was 1/4. So the only situation where you would have the same amount at equilibrium would be if the two kinetic constants would be equal and with the same rate law, obviously. So that's a common misconception, right? We will go through all the misconceptions at some point. So you may have reaction in which the products are prevailing. You have a lot of products by the time you reach equilibrium. You may have, and so the direct reaction is the one that's prevailing. You may have reaction in which by the time you reach equilibrium, you still have a lot of reagent and very few products, in which case is the backward reaction that's the most important. Or sometimes you may have relatively similar amounts. Let's see how the concentrations vary in the process of reaching equilibrium. So in this example, we have a reaction that's A transforming into B and C. So it's a decomposition, basically. And we are assuming that at the beginning of the reaction, so when time is 0, we have a certain amount of A, but we have no B and C. So the rate of the direct reaction that is connected to proportional in some form to the concentration of A, we don't know what the rate law is, but it's not important in this case. We know that the higher the concentration of A, the higher is the rate of the forward reaction. So the reaction at the beginning has its maximum value because we have the maximum concentration of A. After that, the concentration of A will drop as the reaction proceeds because A is being transformed into B and C. So as the concentration of A will drop over time, the reaction will slow down. So you see that the slope of this curve is getting more and more smaller and smaller. Conversely, the concentration of B and C is 0 at the beginning, so the rate is 0. As the concentration of B and C increases during the reaction, the rate of the reverse reaction increases as well. So you see that the slope is going up. Eventually, while this rate is going up, the rate of the reverse reaction has a positive value, a positive slope, while the rate of the forward reaction has a negative slope. So this is decelerating, so to speak, and this is accelerating. So by the time you get, it's just unavoidable that eventually they meet somewhere having the same rate. That was analogous to the situation in the analogy of the coins in the two containers. That would be the situation where the number of coins you're moving from R to P and from P to R is the same. Therefore, there is no net change in the amount of coins that you have in both containers, and the number of coins stay constant over time. So this was happening here. You reached equilibrium, and the concentration of A and the concentration of B and C will not change anymore, even if both reaction, the reverse reaction and the direct reaction, are still happening. At this point, what's equal are the rate of the reaction, not the concentration. In this case, the concentration of B and C would be the same because there is the same stoichiometrical coefficient, but the concentration of A and the concentration of B and C are going to be different. So what condition do we have to be able to reach equilibrium, right? So we need to keep things constant. So the temperature needs to be constant, the pressure needs to be constant, and the concentration should not be altered. So we should not remove substances nor add substances. So if we have gases, the container needs to be closed. We have seen in the analogy of the coins that the equilibrium can be approached by either direction. We had an example where all the coins were in the reagent flask. We had another example where all the coins were in the product flask. And then we had an example where they were distributed between the two. It didn't make any difference. We always ended up with a ratio of 2 to 1 by the time we reached the equilibrium. And it's important that you understand that at equilibrium the concentration will not typically be equal. It could happen every now and then, but is not the rule, is the exception. And the two reactions do not stop because it's a dynamic equilibrium. So, common misconception, and this is important, that's why I'm insisting on it so much, because those are the most common misconceptions, these are the concept that tends to be tested. So you always get a question about this in any, even in the final, especially in the final. So at equilibrium, the reactions do not stop, both of them, direct and reverse. What's equal is the rate of the two reactions, not the concentration of reactant and product. That's typically different. The only K is called K because it's a constant, right? So the only thing, so it's always the same value. The only thing that really could change the value of the constant is change in temperature, and we will discuss that more in detail afterwards. And then if everything that you have in the equilibrium is dissolved in water, and one of the reagent or one of the product is a solid, as long as there is a little bit of solid, it doesn't really matter how much you have, because it's a separate phase. And again, we will talk more about this. This would be what is called a heterogeneous equilibrium, so we are going to talk about that. So how do we write the equilibrium constant? Well, in the analogy of the cone, it was simple. We had just we define K as the ratio between the amount of coins on the product side divided the amount of coins on the reagent side. What if we have a reaction, a chemical reaction that looks a little bit more complicated, right? So this is the usual generic reaction, so where you have A and B as reactant and C and D as products, and then you have a coefficient that's different for each of them, that's represented by the small A, B, C, and D. Now, if you notice, everything is aqueous here, and I put the label red. I wrote the label red, so there has to be a reason for that, right? So that's because it's really important to pay attention to phases in equilibrium. So this is what we call a homogeneous equilibrium, like everything is in the same state, that is dissolved in water. So we start simple, then we will worry afterwards what if something is not in the same phase. But for the time being, let's just focus on the simple scenario where everything is in the same state. Example, dissolved in water. So in this case, we write the equilibrium constant, Kc. C is for, the little c here is for concentration, because we are using concentration to calculate it, because there are other ways. So what you do, it's a ratio, because we've seen that is the ratio that stays constant by the time you reach equilibrium. So on the numerator, on the top of the fraction, you have the molar concentration, like you remember these square brackets with a formula in it, represent the molar concentration, so moles per liter, of the two products. And oh joy, finally, we can actually directly use the coefficient in the balance equation for the exponent. You know, the one that I always told you not to use in kinetics. In equilibrium, we can do that. And then for the reagent, the same thing. You're using the coefficient as exponent. So to write the equilibrium constant, you do not need an experiment. You just need the balance equation. So it tends to be confusing, right? Because we just went through the kinetic unit, and this is equilibrium. So what's different? So to write the rate law of the direct reaction and of the reverse reaction, we cannot use the balanced equation. We need an experiment that tell us what are these exponents here that are not typically the coefficient unless the reaction is an elementary mechanism. in just one step. Instead, we have a constant, right? The constant is indicated with a small letter K, and it does have units. The units depends on the specific order of the reaction. For the equilibrium constant, instead, we have no units typically. So the equilibrium constant doesn't come with units for reasons that are too complicated for this class. And we are authorized to, we don't need to do any experiment. All we need is the balance equation. If we have the balance equation, we can just directly plug the coefficient as exponent. So the equilibrium constant can be written with this subscript AQ, and this is more a generic definition. So is the equilibrium constant, you know that is the equilibrium one also because it's capitalized, but it doesn't refer to any specific, it doesn't take any commitment basically in terms of how I measure the amount of reagent and products. If I write Kc, that implies that the amount of reagent and products is being measured as molar concentration. If I write Kp, then the amount of reagent and products has been calculated in terms of partial pressures because maybe they were gases, right? So we use the one that's more convenient depending on the nature of the reagents and the products. So it's a constant, that's why it's called a constant, right? And so it doesn't matter how much reagent or how much products you have, it doesn't matter what the pressure is, it doesn't matter if you have a catalyst or not, the value, the numerical value of K is always the same. The only thing that would change the numeric value of K is that a change in the temperature. So as I was anticipating, there are different types of equilibrium constant. So the first two is depending on how we express the concentration of the amount of reagent and products. If it's a molar concentration, we use the symbol Kc. If it's if we have everything is a gas, then it's more convenient to use the partial pressures. If we have acids and bases dissociating, so you remember we talked about acids and bases can be weak or strong, and strong acids and bases are completely dissociated, so it's an irreversible reaction, let's say. But while for weak acids and bases it's a reversible reaction, so you reach an equilibrium. And so we use A for acid and B for base for those equilibrium constant. And the last one we will talk about is the SP, solubility product, that refers to the solubility of poorly soluble substance. So one thing that typically tend to be confusing for the students is now it's true that all your questions are going to be multiple choice at this point, but if you would have a more open questions like a short answer, sometimes you are asked to make a certain determination or a certain statement on the equilibrium constant or on the equilibrium constant expression. So when we talk about the equilibrium constant, we are referring to the number, the value, the numerical value. Could be, you know, in terms of concentration or partial pressure. As I say, it's typically used given without units. And oftentimes in the problems, they give you that value with the temperature, at the temperature at which it has been measured. Not because you have to do anything with the temperature in the resolution of the problem, but because the temperature would change the value of KQ, it's more proper, more formal to give the K equilibrium with the temperature at which it has been measured. The expression is the actual formula, the one that I showed you before, where you write the concentration, for example, of your reagents, each elevated to a power that corresponds to the coefficient in the balance equation divided the concentration of the products, each elevated to, and so forth. Let's see an example of a calculation of the Kc. The reaction presented is the Haber reaction to produce ammonia. As I said, that's an example that really comes out a lot. As you see, they are asking you to calculate the equilibrium constant for the reaction at 500 Celsius. Again, as I was kind of anticipating before, it's not like you are expected to do anything with that 500 Celsius, like transform it in Kelvin or use it somehow in the calculation. It's because the equilibrium constant is a function of the temperature and it would change at different temperature. It's proper to always specify at which temperature you are operating, even if you don't have to use the temperature for any calculation. So you're given the concentration at equilibrium, so that's important, and all the amount of all the substances are given as molarity, so concentration. So what you're going to calculate is the Kc. These are gases, so one could have opted for calculating the Kp, but in this case is the Kc. So the first thing you want to do is write the equilibrium constant expression. So you want the formula. And so, and you can do that based on the balance equation because you need the coefficient. So it's going to be products on top elevated to the second power because there is a coefficient of 2, and then reagent at the bottom, each elevated to the concentration, to the coefficient in the balance equation. All you have to do now is plug and check the numbers, and then you come up with an x of 0.0603. Now this is a situation where you are given the concentration at equilibrium. Most of the time, we don't know that. We may know the initial concentration, so what we put in the beaker before that magic nirvana of the equilibrium was reached. And so that typically makes the calculation slightly more complicated, but as I said, we will go one step at a time. So the reason I could plug directly the numbers is because I just want to stress that out. The concentration that I was given were concentration at equilibrium. So when you use this formula, the numbers then you plug needs to be concentration at equilibrium. That are not the initial concentration, are typically different from the initial concentration. So when we did the analogy with the coins, we also introduced the concept of reaction quotient that has the same, calculated with the same formula as K. The difference being that for the reaction quotient, we have infinite value. So it could be any possible combination of amount of reagent and product our fantasy can come up with. And those were all, for example, the initial concentration in the analogy and all you observe that the value of Q was changing over time. But eventually they were all converging to the same value. So that unique value is K, the equilibrium constant. So when you reach equilibrium, Q is going to be equal to K. Sometimes you start from a situation, let's remember the example of the coins, where Q is too big, then Q needs to go down slowly until it reaches K. If Q is too small, it will have to go up. So by looking at the value of Q, we can tell if we are at equilibrium or not, and also we can tell in which direction, which of the two reactions needs to become prevalent, so in which direction the equilibrium needs to shift in order to reach the equilibrium. This is a problem where you're provided with pictures that are supposedly helping you to figure out the solution. And this is a type of question that is quite popular, so you might expect something like that to come up in the final, not necessarily about equilibrium, but in general, question with pictures. So you're given the reaction, the reaction is balanced, and you're given the value of the equilibrium constant is 1/3. So you have three different scenarios independent from each other, and each represent like a picture of a situation where you have a certain amount of each of the four species. And the question is any of those three scenarios representing a situation of equilibrium? So first you need to identify who is who, so to speak. So you know that you have one of the two reagent is a bimolecular compound where you have a bond between two identical atoms. So you're looking for molecules with the same colors in a B-atomic molecule. So that would be, there is no blue and blue, so there is only a purple and purple. So we know that that represent A2. Therefore, when you have A alone is the purple one, and when you have the blue alone, that has to be B by exclusion. And finally, AB is obviously the one with the with both colors in the same molecule. So now that we know that, we can write the equilibrium constant expression. Okay, so you need to take the concentration of the two products elevated to the coefficient. Now all the coefficients here are 1, so we don't expect to have write any exponent, divided the concentration of the two reagents. So it would look like that. Now these are molar concentration. You really don't have that information here. You can just make an assumption, let's say that that this container, these blocks, correspond to 1 liter of volume, and each of these icons, each of each drawings represent 1 mole. So basically all you have to do is count each species and plug that number in the formula. So for the first scenario, we have 3 molecules of A, 1, 2, 3, 5 molecules of AB, 1, 2, 3, 4, 5, so that's 15, and then we have only 1 B and only 1 A2, so it's 15 divided 1, 15. So 15 is a number that's way larger than the value of the equilibrium constant. So this is a situation where Q is too big and has to decrease. For Q to become smaller, we need to make smaller this number or larger this number. So to make this number smaller, we need to have less of the products, so the reaction needs to shift in this direction. For the second reaction, the second scenario, sorry, we have, let's see, 1A, that is this little fellow here, and then we have 3AB, 1, 2, 3. And then we need to count A2, and there are 1 and 2 of those, and 3. And then we need to count B, 1, 2, 3. So 3 and 3 is 9. So 1 divided 9, 3. So the 3 divided 9 is 1/3. So this corresponds to equilibrium. So for this scenario, number 2, we are already at equilibrium, so the reaction doesn't have to change at all. Scenario 3, we have, so let's see, we have of 2 of A, 1 and 2, we have 2 AB, 3 AB, 1, 2, 3, 4, so we have 4, so it's 2 times 4, 8, and then A2, we have 1 and 2, and B, that's the blue one, 1 and 2. So it's 2 times 4, 8, divided 4, 2. So 2 is still too large, so it's exactly the same situation as 1. Q is too big, we need to move the reaction in this direction. It's less dramatic, the difference is less dramatic than in 1, but it's conceptually very similar. So the answer was the second one. In order to determine if a reaction is at equilibrium or not, we need to evaluate the value of Q for the concentration that we are given and compare it with K. If Q is too small, that means if you consider how we calculate Q, right? So we have at the bottom of the fraction, we have the reagents, and at the top we have the product. So if Q is too big and we want to make it, we want to increase it, we need to increase it the top of the fraction. So the reaction needs to proceed in this direction, so that the concentration of H2O and carbon monoxide goes down, and the concentration of H2 and CO2 goes up until we reach equilibrium. So that would be a situation that corresponds in this graph to this point and this point. So we are starting with exclusively, for example, only the two reagents, and we have no products. So that means that the numbers here on top would be zero, on top of the fraction would be a 0. So basically the reaction quotient is 0. So that's as small as you can possibly get, right? So what's going to happen is that as the reaction proceeds, the concentration of the H2O and of the carbon monoxide is going down. The concentration of the H2 and the CO2 is going up. This is going to make Q larger and larger until eventually Q reaches the same value as K, at which point the concentration of every species will stay constant over time. The reason they put this gap in the time line is because it will stay indefinitely constant. If Q is too, let's use a different color, if Q is too big, we need to make, it means that the quotient is too large, we need to make it smaller. The way to make it smaller is to have less hydrogen and less carbon dioxide and increase the level of water and CO. So we want to push the reaction in that direction. This would make Q getting smaller and smaller until it will reach the same value as K. So that corresponds in this graph to these two starting points, right? So we have just the products, H2 and CO2, so that concentration is at its maximum level, and the concentration of the two reagents is 0. As we will have the reverse reaction happening, and this will decrease the amount of hydrogen and CO2 and increase the amount of water and carbon monoxide until again we reach the level of equilibrium, at which point the concentration are going to stay constant over time. If by accident Q is equal to K, then we are at equilibrium and we are already in this part of the graph, so nothing will happen basically. Now this may kind of look similar but at the same time different to another graph that we saw before, and so I don't want that to create confusion. So this is the graph that you might remember, and what can generate some confusion is, let me get the pointer, is that in here there was one function is going up, the other curve is going down, and eventually they become the same curve, so they overlap. While here there is this huge gap between, right, the two curves, but they are both describing reaching equilibrium. So how come they're different? Because if you pay attention, what's on the y-axis is different. Here you have the reaction rate, here you have the concentration. So at equilibrium, what becomes identical is the rate of the forward and reverse reaction, but the concentration are typically quite different. So that's why these two curves are not overlapping and this curve is overlapping. So let's see an example. They're asking us if this reaction is at equilibrium. Of course, we need to know the value of Kc. So the value of the equilibrium constant is 5.6. And we are given a particular set of concentration, one concentration for each species. So in order to determine if the reaction is at equilibrium, we need to calculate Q, the reaction quotient. In order to calculate Q, we need to be able to write the expression of the quotient. So that's the formula that you use for calculate both Q and K. So the only coefficient is the one in front of hydrogen, so the concentration of the hydrogen needs to be elevated to the third power. So all we do is plug the numbers. The 0.8 needs to be at the third power. We get a value of 12.8 that is larger than 5.6. So that means that the value being too big, we need to reduce the top and increase the bottom. And this can be done if the reaction proceeds in this direction. So basically there is too much product, and the reaction must shift to the left in order to reach equilibrium. As we have anticipated before, there are two types of equilibrium depending on the phases of the species involved, if they are all in the same phase or if they are in different phases. So, for example, in the first case, the reaction between water and carbon monoxide to form hydrogen and carbon dioxide, everything is gas, so this is an homogeneous equilibrium. The two examples below instead are examples of heterogeneous equilibrium, because as you can see, for example, in the first one we have calcium carbonate that is solid while everything else is aqueous. And in the second example, so that's the dissociation in aqueous solution of a salt that we have classified as insoluble in when we learn the solubility rules. Solubility rules are very categorical, meaning we classify things as either soluble or insoluble. Things are rarely so divided in such clear-cut categories in nature, and normally there is more of a continuum, and this is the same, and it's just the same for solubility. You go from very soluble substances to poorly soluble to almost insoluble substances. So whenever a salt is dissolved in water and you have a saturated solution, so you have the presence of the solid salt at the bottom, on top you have a saturated solution, and there is an equilibrium happening between the amount of salt that is precipitating at the bottom, so that you can see as a solid deposit, and the amount that is actually dissolved, that you cannot see, but those are the ions in solution. This is called the solubility equilibrium, and is heterogeneous because the precipitate at the bottom is a separate phase, is a solid, and as long as there is some, that's all that matters. The actual amount does not affect equilibrium, because the concentration of the solid in itself is a constant. Calcium carbonate precipitate at the bottom of the beaker is not dissolved in water. It's a solid in itself, so it's a separate phase, and its concentration is constant, 100%, as long as there is a little bit of it. In the second example, you have the dissociation of a weak acid, right? You remember there are 6 or 7 strong acids, but hydrofluoric is not among them. If you remember, hydrofluoric acid is the acid from Breaking Bad. In this case, everything is aqueous except water that is liquid. So this is again an heterogeneous equilibrium. The concentration of water in itself is going to be constant over the whole equilibrium. It's important to identify if an equilibrium is heterogeneous or homogeneous, because that's going to affect the way you write the equilibrium constant. So when you write the constant, solids, liquids do not appear. So if everything is aqueous and there is a liquid, you will not write the liquid in the equilibrium constant. If everything is aqueous and there is a solid, you will not write that in the equilibrium constant. So water typically is not written unless it's a gas in a reaction with other gases, like the one we saw before. Let's see some example of how to write the equilibrium constant using the same equation that we have used in the other slide. So for an homogeneous equilibrium, as usual, you write the concentration of the two products on top and the two concentration of the reagents at the bottom. In this case, all coefficients are 1, so all exponents are 1. When you have an heterogeneous equilibrium, you basically drop everything that's labeled as solid or liquid. So the first constant is going to be written as a product between the concentration of the calcium ion times the concentration of the carbonate ion, and that's it. For the second, and we're going to call it KSP from the initial letters of solubility product, because it refers to an equilibrium of a poorly soluble salt that's in equilibrium with these ions. For the second one, there is an acid dissociation in water. We're going to call it Ka, A from acid, and we're going to exclude water. So the only product, the only reagent that will appear at the bottom is going to be the HF, and water is not going to appear. This is another example. This is an oxidation reduction, and we will see a lot of that in the next unit. That's going to be electrochemistry. So solid copper, metallic copper, in the presence of silver ion, is going to get oxidized. So silver has the ability to pull away electrons from the copper. And in fact, if you remember, in the reactivity scale of metals, silver is lower than copper and is more resistant to oxidation and tarnishing. So we have, on the reagent side, we have a solid copper. We also have a solid on the product side, that's the silver, and then we have two species that are aqueous. When we write the equilibrium constant for this reaction, only the aqueous species will appear. So you will not see copper solid or silver solid, because those are in a different phase. So you have a little piece of copper and a little piece of silver, and those are not dissolved in water. So there is doesn't make any sense to talk about the concentration of those two metals as neutral metals in the water. They are concentrated. If anything, you should consider the concentration of them in themselves. That's always going to be 100%. Let's see what happens if you combine equations. So in this case, you have a sequence of two equations, and if you put them together, the equation at the bottom is the sum of these two. Now, we can obtain the total equation by adding the two sides of each single equation and crossing out things that appear on both sides, like as if it was algebra, basically. So what would be the equilibrium constant for the composite equation? So, or what happens if you take an equation and you multiply everything by 2, for example. If you remember, we had similar issues, let's say. We talked about a similar situation when we were talking about thermochemistry. And when we were applying the Hess's law, we were manipulating equation by multiplying them, dividing them, reversing them, right? So we learned the rule for thermochemistry. For the delta H of reaction, so the heat that is exchanged during the reaction when the reaction happens at constant pressure, if we reverse a reaction, the delta H is going to be same number with an opposite sign. If we do a multiplication, we have to multiply by the same factor, the delta H. If we divide, that would be like multiplying by 0.5. We need to divide by the same number, the delta H. If we combine a set of reactions, the total delta H is going to be the sum of the individual delta H, and that's the Hess's law. What about equilibrium constant? Unfortunately, it's similar, but different enough that you can get confused. Okay, so when you are reversing a reaction, the equilibrium constant of the reverse reaction is going to be the reciprocal. Basically, it's like shifting from adding, subtracting to multiplying, dividing. So if you are doubling the reaction, you need to square. So if the reaction is multiplied by 2, the new equilibrium constant is equal to the old one elevated to the second power. If you would be multiplying by 3, you would have to elevate to the third power, and so forth. If you are dividing by 2, then you have to take the square root. If you are dividing by 3, you have to extract the cube root. If you are combining a set of reactions, the total equilibrium constant is the product of the individual equilibrium constant. So this is a bit of the summary of all the things you need to know to be able to write the equilibrium constant, because let's say the whole elevating to the power and taking the root gets relatively complicated to deal. Basically, the vast majority of the questions that you get about this type of stuff, they just multiply by 2 or divide by 2, so that is easy to do the math on your calculator. So let's see some examples. We are asked to write the equilibrium constant expression for the reaction between hydrogen iodine and forming hydrogen iodide. The value of the constant is 2.5. Now, the first thing you want to ask yourself is if the equilibrium is homogeneous or heterogeneous. Everything is labeled as gas, and therefore it's a homogeneous equilibrium. That's important because it tells me that when I write the equilibrium constant, I need to write all the species. In theory, because everything is a gas, I could write two types of equilibrium constant. I could write the equilibrium constant in two different ways, either in terms of molar concentration or in terms of partial pressure. Because the constant is given as Kc, that tells you it's going to be in terms of molar concentration. Remember that Kc has no unit like Kp. In general, equilibrium constants do not have units. So first thing we want to do is write the Kc expression. So we put the hydrogen iodide at the top, elevated to the second power because there is a coefficient of 2, and we divide by the concentration of hydrogen and the concentration of iodine. And we know that that corresponds to the value of 2.5. In the second equation, we need to calculate the Kc, so we need to figure out the number for this reaction. How this reaction compares to the one we have on top. It's flipped. What was the product is now the reactant and vice versa. So what's on the left is now on the right, and what was on the right is now on the left. So when we flip the reaction, remember, if we were wondering about the delta H, we would have to change the sign. But because we are wondering about the Kc, we need to use the reciprocal. So the reciprocal of 2.5 is 0.4. In the third question, the reaction appears to have the same orientation, let's say, so what's a product is still a product, and same for the reactants, but all coefficient has been multiplied by 2. So if I would be doing the math for the delta H, I would have to multiply the delta H of this reaction would be twice as big as the delta H of the original reaction. But because I'm actually calculating the KQ is going to be equal to the KQ of the original equation, 2.5, elevated to the second power. So that gives you a 6.25. So this is the last slide. The next video is going to be about the Chatelier principle, and then we should be done with the equilibrium for this week. Next week we will cover some special instances of equilibrium, and we will also start thermodynamic.